Alright, so this is take 2. I messed up on the first one. You won't see the first one. So I'm going to basically reiterate what I said before. Let's say you're given the function f of x, right? We're going to do your function. F of x equals x cubed like that. You want to find the Riemann sum over, well, you want to find the Riemann sum. That's basically what you're doing. You already said you know integration over the interval 0 to 8. I'll put that in there. So you're trying to find the area of this. With integration, it's pretty easy. That kind of sucks that you have to do it through this way. Do you want your chair back?
No, that's what you got.
Okay, all right. But integration of f of x dx like that equals, this is basically going to equal x to the 4th over 4. The way, there's a rule where if you have some integration, right, it doesn't matter over the interval of x to the n dx like that, it'll equal x to the n plus 1 over n plus 1, right? So you think, well, that's a little weird, but if it makes a lot of sense. Think about it if you took the derivative of this, right? You'd bring the 4 down, it'd be 4x divided by 4, or 4x cubed divided by 4, and it would equal x cubed. So it makes sense, right? So now you have your integration. You can actually, in order to find the area under the curve, it's really easy. You literally take your integration, whatever you found, and you evaluate it from 0 to 8, like this. Basically, all that means is you're going to take 8 and plug it into the function, and then you're going to subtract it from putting 0 in. So it's basically just going to be, if you evaluated this, this is going to equal 8 to the 4th over 4 minus 0 to the 4th over 4. So really, it just equals 8 to the 4th over 4. I'm not going to do it. I don't have a calculator. Actually, I do. I'll do it for you, just so you get a general. You can do it. I know you can. I'm just curious because this is going to help later. Divided by 4. So you get, according to the calculator, you get 1024. That's a huge number, but it's an area under an x cubed graph. So it kind of makes sense. Looking at it in the big picture, right, we're going to draw basically what you're looking for. I'm going to draw it pretty big just so that way I have a general idea of what I'm trying to do. And then, yeah, we'll go from there. Right, so this is an x cubed graph. I'm not really caring right now about, I'm just looking at a general shape of an x cubed graph. That kind of looks like it, right? That's close enough. We're not really caring about this part because this is not in our interval. We'll just label this, that's 0, 2, 4, 6, 8, right? I'll just make it simple. So we're trying to find the area like of that from here to here, right? The way we're going to do that is, I'll do it a little bit bigger since we're only focusing on this part, right? Kind of looks like that and shoots up really high. We're going to try and find little baby rectangles that basically touch the graph at one point and then come back down like that. I have a feeling you probably already know this, but I'm just reiterating basic stuff. Now, the reason why this Riemann sum kind of works is because each of the width, so every rectangle in this section, every rectangle that I drew is going to actually have an equal width. So in this case, we're going to label it as delta x. It's not going to change. Well, it'll change, but it's the separation of each is not going to be different from one another. That plays actually a big role, or else we wouldn't be able to do this, because then we'd be like, well, we'd have to take individual rectangles and it would be a pain, and that's just not fun for anybody. So now we know that it's delta x. You already knew that. I'm just stating it again. You're evaluating it from 0 to 8, right? 0 to 8, we're just doing a basic number line. There's going to be little rectangles in here that go up different heights. And so basically, you want to figure out how to break this into like sub-intervals, right? And the way you can do that is you can take the two ends, and subtract them from each other. Obviously, the bigger one goes first. So 8 minus 0 over the number of widths, little delta x's. I call it widths and delta x, basically the same idea. So your little widths of each little partition or each little rectangle is gonna be 8 over n. That's gonna equal your delta x. So now you're thinking, okay, well, that doesn't really help that much. When we're looking back at the Riemann sum, this, right, I equals 1, x to the n, f of x sub n times b minus a over n. And b minus a is just your interval, your two n's, right? If you had an interval from a to b, this is just a very generic way to write a Riemann sum. This is like a overall, not applying to any specific function. So I'm going to show you my notes as well, because this is going to help me as well as it helps you. So I took, as I showed here, right, generic interval. Delta x is equal to the start, or the finish minus the start, over the number of basically partition or pieces that you'd like. So example, back to this original function, evaluate from 0 to 2, I'm going to take 2 minus 0 over n equals 2 over n. And you know, that's really going to help you. So now we need to figure out, how are we going to figure out the height? Because a Riemann sum is literally just taking the summation of rectangles. So we found our delta x. We found our base of a rectangle. Now we need to find the height. Well, as it turns out, as these rectangle widths get really small and the number of ends increase, this is basically going to approach kind of like a line, right? If let's say n is equal to 2, then you're going to have two rectangles in the interval of 0 to 4, or 0 to 8, I'm sorry. So it would be one rectangle would take up 4 spaces, or 4 units to the right or the left or whatever. But as we make n really big, it means that the widths are going to decrease because there's more rectangles in the interval, right? That makes sense, because like the more rectangles, you got to squeeze them in. You got to keep squeezing them in and in and in, and that's how you find the interval, is because it ends up being actually a line with some delta x, change in x, and then all we do is we take that, right? Because this is some x value we're given, or we have. All we have to do is plug it back into the original function, which in this case is just x cubed. So therefore, the height should equal some f of x. Like this would be f of delta x, like that, right? We don't know what delta x is, but we know it's that. I'm gonna go on the next page and kind of show you what I mean, because my hands are getting crowded. So, right, we have our cube function, whatever it looks like. It doesn't need to be. I'm not doing this really nice. It's very out of scale, but that's not the important part. So you have some x cubed function. We don't need to worry about any of this around here, because this isn't in our interval. So don't even care about it. So we have our rectangles, right? Blah blah blah. Equidistant apart. Let's assume that they're all have the same delta x, like that, right? And that's like 1, 2, 3. That's 5 rectangles you have under this curve. And that's a pretty general area. You could find the area pretty well. However, you still have these little triangles in here that is just free space that we're not accounting for. So when we make, this is delta x, right, for each, blah blah blah. This is all delta x, same distance, same width apart. As we make n really big, we'll see that these triangles, their bases are going to get very small, which means that in the end of this, it's just going to look like this. It's going to look like tiny little, it's going to look like lines basically next to each other all the way down. So you're given some x point on this function, right? X here, x sub n, right? It doesn't matter. Well, the corresponding point where it hits the graph is going to be f of x sub n, because you just plug it back into the function. It's just a point. It's just an x point. So we can back write x sub n. We're going to rewrite the Riemann sum for this summation I index equals 1 of n of f of x sub n times, in this case, in our case, it's going to be 8 over n, like so, like that. Now, what's our function? Our function, f of x, is equal to x cubed, like so. So this is basically going to be like x sub n cubed. Now that doesn't really solve anything because we don't know what x sub n means. So we can write, based on my notes, if I find it, we can find a general way to figure out x sub n. So let's look. You find x sub I. That's the only thing that changes in this case because it's the starting point plus I width or initial position. So basically, in this case, I'm looking for it right now. I apologize. F of x sub I see. Okay. Okay, I understand what's going on. So we need to what? Hold up.
You have my vape?
Yeah, I do.
Alright.
Alright, shut the door on your way out.
Okay.
I'm trying to show something. So now we need to figure out, well, what is that? Like, what is x sub n? You don't know what it is. You'd have to plug back in this 8 over n into this function, and it's just going to be a pain in the butt because it's going to be different. So the way, according to my notes, the way I wrote it, see how I have that here? F of x sub I delta x is equal to the summation of the interval delta x times I. And I in this case is right here, right? I is equal to 1, I could equal 2. But that's basically what you're going to do. So I'm a terrible teacher. I can do this out, but I can't really show it because I barely know what I'm doing. Shouldn't be taking this lesson from me. But summation n I equals 1. You have f of x, 8i over n, like that. 8i over n times 8 over n, like so. Now you're going to take that and you're going to cube it. So you're going to do 8i over n cubed times 8 over n. Summation of this. Now, there are some properties of doing summation that I have here, and I'm basically just gonna pull out everything except for an I cubed, because what's gonna happen is I itself has some really weird things it's gonna do, and there's actually a couple formulas that I have written down that'll basically like do this, like basically just like finish this. So I'll show you them right now. So let's say f of x, or the summation of I, is equal to n times n plus 1 over 2, right? 1, 2, 3, 4, n. I squared is equal to that, and I cubed is equal to that. So what I'm gonna, see that? That's nk. This is what summation is, basically. I don't know why that is. I just learned that. It's just kind of how I figured it out. So if I'm looking back at my notes, right? We're in this stage now, right? We squared both things, and then what we're gonna do is we're basically gonna multiply everything together and then pull out all of our everything else except I. So in this case, right, it's gonna be 8 cubed I cubed over n cubed times 8 over n, like that. That's going to equal that. We're just cubing everything in here. So what I'm going to do is I'm just basically going to fast track this. I'm not going to multiply everything out because we know that this is 8 to the 1 and that's n to the 1. So I'm gonna just do basic exponential properties and manipulation. So I'm just gonna, if the bases are the same, I'm gonna add the exponents. So this is gonna equal 8 to the 4th I cubed over n to the 4th, like that. I'm gonna pull out everything except for I, so I get 8 to the 4th over n to the 4th I cubed, like so. Remember, we still have this sum over here, and I equals 1. And then I'm going to move over to the next page. We're not going to worry about 8 to the 4th over n to the 4th right now. What we're really going to worry about is I cubed. That's what I'm really thinking about right now. The summation of I cubed and I equals 1 is equal to, according to my notes here, right? Is equal to n times n plus 1 all squared over n. Oh, over 2, I should say. I'm sorry. So overall, this is going to equal n squared times n plus 1 squared over 4. Now that we know that, we can take I cubed and we can put what we figured out here back into I cubed, into the summation, into everything. So writing it nice and neatly and clean, summation I equals 1, and you're going to have 8 to the 4th over n to the 4th times n squared n plus 1 squared over 4. And now we can do basically some simple like manipulation again, simplification. So 8 to the 4th, we're just going to write this out because this will help me in a little bit, times n squared times n plus 1 squared all over n to the 4th times 4, like that. Right, we're just combining everything. So this will cancel, that'll become 2, and that'll be completely gone entirely. So now we have 8 to the 4th times n plus 1 squared over n squared times 4, like that. This is the time where we have to bring back in the, hold on. This is the time where we're going to bring back in our limit. You have to remember that any Riemann sum, I forgot to add this, any Riemann sum, I'm just going to write the generic equation, I equals 1. You're taking the limit as n approaches infinity. That's what I was talking about before. As n gets really, really big, these widths are going to get really, really small, and they're going to act like lines. And that's how you find the area. It's a lot easier with integration, but since your teacher's kind of an asshole and making you do it this way, f of x sub n delta x, like that, you're basically going to take the limit here. So what I'm going to do is I'm going to keep 8 to the 4th as it is, because it really doesn't matter in the end, because it's still going to equal the correct answer. I'm going to move the just basic numbers, coefficients, out to the front of this problem right here. So I have 8 to the 4th over 4 times n squared times n plus 1 squared. And now what I'm going to do is I'm going to distribute this. I'm going to FOIL all of this out. So I get 8 to the 4th times n squared plus 2n plus 1, like that, all over 4n squared. Right? You see that? Now I'm going to bring everything, I'm going to combine again. 8 to the 4th n squared plus 8 to the 4th 2n plus 8 to the 4th, and this is all over 4n squared, like that. See that? We still have to remember the limit as as n approaches infinity. That's basically what you get after all of this work. That's what you get. And now what I'm going to do is I'm basically going to split this up into multiple different terms. So I get 8 to the 4th n squared over 4n squared plus 8 to the 4th 2n over n squared plus 8 to the 4th over n squared. Like that. Right? We can do that. That's just basic. That's basic algebra. I'm not even sure it's algebra. It's basic math. Keep writing x. That's n approaches infinity. So we look at this. We look at this in the beginning form, and we see, oh shoot, that's infinity over infinity. That's not going to work. That's an indeterminate form. We don't know what it's going to do. Well, when we break it off like this, we can see that the n squareds cancel out like that. This cancels out with that, and that stays. So in the end, the limit as n approaches infinity is equal to 8 to the 4th over 4 plus 8 to the 4th times 2 over n plus 8 to the 4th over n squared. Now all we simply have to do is plug infinity back in. Well, this doesn't have an n, so that stays the same. This is going to be some random number. This is going to stay the same. We're plugging the limit back in. I'll write it down. Is plus 8 to the 4th times 2 over a huge number, right? Some giant number, because n is approaching infinity, plus 8 to the 4th over a huge number squared. So basically, this is going to be approaching 0. This is also going to be approaching 0, so we can just assume that it's 0. And in the end, we get 8 to the 4th over 4. Now, looking back originally at what I showed you with integration, we have the same number. So, reiterating back what I said, think of the concept as n gets really, really big, the delta x's, or the widths, get very, very small. And the more precise points you get, the smaller area of triangles you have here, right? There's not a lot of triangle space, hypothetically, when we're just shooting a line at every single point down this curve. I don't know if I taught this really that well. This took me 23 minutes to do because I'm trying to explain it. I hope that I can send this to you. If not, I'll share it with you. And so, yeah, watch this. Fast forward through it if you want. But, yeah, that's how you do a Riemann sum. I don't know about a midpoint Riemann sum. I'm assuming just breaking it up into 2 different intervals is the same thing. However, I am not sure. So, yeah. Coming at you straight with some really, really shitty explanation. I could do it better in person. I'm sorry. If we have time tomorrow, I'll try to. But yeah. All right, get some rest. And yeah. Kisses.